Welcome to Derivability. Today we're going to take a look at an approach to Snell's law that involves wave properties. Okay, and what I'm thinking of is what we call a classical approach to Snell's law that is something that doesn't involve quantum physics. Okay, ultimately we get refraction the way we do because of properties of essentially electron density in atoms and when a light wave changes medium. Okay, we're not going to talk about that. Today we're just going to think about how wave properties in general create this phenomenon called Snell's law, or rather I should say refraction, which then leads to a bending of a light ray, or really any wave when it changes medium. Okay, so what we need to do first is talk about what refraction is. Okay, and fundamentally, it's the speed of a wave changing when the wave changes medium. Okay, now again, a lot of folks, and they're not completely wrong, will say, well, I thought it was the bending of light. Well, that is caused by this change in speed. Okay, so let's take a closer look at a few things, and then we'll eventually get to this bending phenomenon. It's going to help to talk about some notation. Okay, so let's use the letter C to stand for the speed of the wave that travels, if we're talking about light waves, that travels in empty space, or sometimes we say a vacuum, and V for the speed of a wave when it travels into some sort of material medium. Okay, so V is always going to be less than C, if even just by a little bit. So for instance, the speed of light in a vacuum is what it is. We often quote that as 3 times 10 to the 8 meters per second. Okay, that won't be important, that particular value for our discussion today. It's actually a little bit smaller than that. Sometimes textbooks will write that as 2.998 times 10 to the 8 meters per second. But when light travels even into air, there's a slight slowdown. Okay, so we'll use V to stand for the speed of wave in some other material medium. All right. Now, because these numbers are going to be so big, in terms of meters per second, 10 to the 8 something meters per second, it's handy to define a unitless quantity called the index of refraction for that medium. Okay. N equals C over V. All right, so when you're doing homework problems using Snell's law and other things requiring this index, that number N will usually be in a table in the chapter of that book that you're doing the homework from, or I'm sure that lists of indexes of refraction are just all over the internet. Okay, now it's going to be handy to rearrange this equation for the index of refraction to come up with some relationships about speeds and other things when a wave changes medium. Okay, if we solve that index of refraction equation for C, which is a constant, we get N times V. Okay, well, what that means is that the product N times V is just going to be the same no matter what, because it's equal to this constant C. Okay. All right, so we can say N1 times V1 equals N2 times V2, because they're both equal to the same constant C. So whenever a wave changes medium, the product of its velocity times its index of refraction is always going to equal a constant. Okay, and we can sometimes don't worry about that constant. It's equal to C, but is what it is. Okay. All right. Now the big next question, before we can really talk about the bending of light and coming up with Snell's law, is well, how do certain other wave properties change? Okay. So for instance, we might be interested in how the wavelength changes when a wave changes medium, or possibly the frequency of the wave. Okay, if those how those change, if at all. Okay, so let's talk about some of that next. In particular, let's talk about frequency. Well, the frequency of a wave is determined by the source of the wave, and that's all. Okay, the frequency is unchanged by a change when the wave changes medium. Okay, so the frequency does not depend on the medium. This is kind of subtle. It's not necessarily an obvious thing, but if you remember what frequency is, it's the rate of oscillation, not like in meters per second, but in cycles per second. You know, it's the rate at which, if you like, wave crests are being produced at the source. And that just is what it is. You know, you're not going to change the rate of crests production, if you like, or troughs, you know, cycles, just when you change medium. Okay, so that's going to be a very helpful thing to know here in a minute. Okay, so what we can do next is we can think about how the wavelength of a wave changes, and we'll do that using a very well-known formula for waves. Okay, well, here's that formula. You've probably seen this somewhere before. Velocity equals wavelength times frequency. Okay, if you're interested in light waves, you've probably talked about just waves in general before, sound waves. Okay, we know this to be true for waves in general. Okay, and what I'd like to do with this is use this equation along with the relationship between the indexes of refraction and the velocity. Okay, keeping in mind that the frequency of a wave is constant, doesn't change when the medium changes. Okay, so let's take a look at that now. Okay, so placing those two equations together with the parentheses there to emphasize, that's where the velocities used to be. Left side, N1, lambda 1 F1 equals right side N2, lambda 2 F2. But remember, the frequency of a wave doesn't change when a wave changes medium. Okay, so these frequencies, I've got them labeled F1, F2 just kind of for convenience, but they're equal. They don't need the subscripting. They can cancel out. So from that, we get a very handy relationship between the wavelengths. Okay, so there you see what that relationship is. Okay, to me, kind of the nice thing about this relationship between the wavelengths when a wave changes medium is it's essentially the same equation as for the velocities, except you're just substituting in the wavelength there. Okay, so it looks like that if the velocity is smaller when a wave changes medium, then the wavelength will be smaller as well. All right, so now is when we want to get to a diagram and take a look at what has to be true for the direction that the wave travels when a wave changes medium. All right, so here's a diagram we can start with to try to figure out the rest. Okay, so the black vertical line represents the boundary between two different media. On the left, medium number 1, which has its index of refraction, speed, wavelength, etc., and then medium number 2 on the right. Okay, the horizontal dashed black line, this is something we call the normal line. Okay, and that is perpendicular to the surface. Okay, that's maybe you've heard of something called a normal force before. That's perpendicular to a surface. Okay, this isn't a force. It's just a geometric thing. It's perpendicular to the surface. Okay, but what we do is we measure the angle that the ray makes with respect to this normal line. Okay, I've drawn that as theta 1. Okay, sometimes we call that the angle of incidence. All right, so let's try and figure out what happens to this wave when it crosses over into the new medium based on the wave properties that we've been talking about. Okay, now the red lines that are perpendicular to the incident ray, those are called the wave fronts. Those were where for instance, where the crests would be. Okay, it's, we don't have to talk about them as being crests, but just some constant phase position of the wave. Okay, so crest is a good way to say it. Okay, so we want to figure out what happens first to these wavefronts on the right side of the boundary. Okay, well, we have to obey two things that we know about waves. Let's assume that V2 is less than V1, which means that lambda 2 is going to be less than lambda 1. Okay, so we have to draw those wavefronts closer together over on the right side of the boundary. Okay, But we also need to make sure that wherever we have a wavefront crossing from the left, it's attached to a wavefront on the right. Okay, this is kind of a subtle way of saying that the frequency has to be constant. Okay, you can't have a wave kind of entering that boundary and not exit that boundary at the same point and at the same time. Okay, well, it turns out there's one way to do this. Okay, and that is if we take these wavefronts attached to, where they're supposed to be attached to here, and if we kind of angle them upward just a little bit. Now they have to be parallel with each other. Okay. And they're supposed to be the same distance apart. So pardon my lack of artistic skill here, if that's not so. At least not exactly. Okay, well, what this permits us to do now is to draw the new light ray. And it has to be perpendicular to these wavefronts. Okay. All right, so this we might call the refracted ray. Okay, sometimes we call it the transmitted ray, but it makes its own angle with respect to that normal line. Okay, I'll call that theta 2, sometimes the angle of refraction. All right, so now what we want, well, first of all, hopefully I've convinced you that the light ray has to bend. Okay, if these other things that we are assuming now are true. Okay, well, now the big question is, let's see if we can get a relationship between theta 1 and theta 2. Okay, now to do that, I'm going to draw in another incident ray from the left, parallel to the first one. Okay, maybe something like that. And likewise on the right. Okay, for the refracted ray. Okay, now what we have done here is we have created a pair of right triangles. And I'll kind of outline them. Okay, and then draw a separate diagram where we can work with those. Okay, before I draw that separate diagram, try to convince yourselves that if this angle is theta 1, right there, then so is this one. And if this angle is theta 2, then so is that one. Okay, and again, another very important thing here is that these two triangles, they're both right triangles, they share a common boundary along the boundary between the media. All right, so let's get that those triangles sketched, and we should be able to finish this off. Okay, well, here's our pair of triangles that share that common side along the boundary between the media. Okay, I think maybe I forgot to mention that what the wavelengths were in the picture. Maybe you saw that, but the distance between the wavefronts were the wavelengths on the appropriate side of that picture. Okay. All right, so with a little inspection here, you can see that on either side of the picture, we have sine theta equals lambda over d. All right, now we have a situation similar to what we did previously where we have a constant in there. Okay, we have this d. Okay, and that d is the same. Turns out it's the hypotenuse for each triangle. It's the same. So we can actually move this forward if we solve for d. Or actually, it's going to be a little more helpful if we solve for 1 over d. So let's take a look at that next. All right, so if we solve this equation for 1 over d, which is a constant, we get sine theta over lambda. Of course, it doesn't matter if it's theta 1 or theta 2 because d is a constant. Okay, so we can write this equation with a theta 1, lambda 1, theta 2, lambda 2. Okay, and so we can just kind of forget about d at this point, and we have sine theta 1 over lambda 1 equals sine theta 2 over lambda 2. Okay, now in some sense this is what we were looking for, except it's sometimes you just don't know what those wavelengths are. Okay, or you don't even know either one of them. Okay, so let's do this. Let's multiply through in the denominator of each by the frequency of the wave, and we can be sure that we don't have to worry about F1, F2. Of course, if they were different, we couldn't do this algebra step. But since they're the same, let's label them as F. Okay, and then F times lambda is the speed of the wave. Okay, so that gets us to our next step. Okay, next step, we have sine theta 1 over V1 equals sine theta 2 over V2. Okay, maybe a little bit better, a little bit closer. Okay, but again, you may not always know these V's. They're large numbers, times 10 to the 8 meters per second. All right, so now let's multiply both sides of the equation by the speed of light out in a vacuum, c. Okay, again, that's algebraically permitted, but what we can do is we can think of these fractions here, c divided by v. Okay, something like that. And we know that c divided by v is the index of refraction. So that gets us to our final step, and we'll be about finished. Okay, so there we go. We have n1 sine theta 1 equals n2 sine theta 2, and that's what we are looking for. That is what is most commonly called Snell's law. Okay, the relationship between the angles in what is commonly called a refraction problem. Okay, where we have light bending at the interface between two different media. Okay, now just a few closing remarks here. One is, other than using some notation and ideas that come from light waves, we didn't really talk about the wave being light. So, to the extent that we can apply the idea of an index of refraction to any kind of wave or a sound wave, then this is true for any kind of wave. It's very general that way. Okay, also, there's another approach that's actually common in textbooks at the introductory level that uses Fermat's principle of least time. Okay, and in the near future, I'm hoping to make a video on that and how that reproduces Snell's law. Okay, now for those of you who are looking at this from maybe a little bit more advanced perspective, okay, light, as you know, is an electromagnetic wave. Any electromagnetic phenomena, waves or electrostatics or what have you, Faraday's law, all these things are governed by Maxwell's equations from electromagnetism. So it turns out that Maxwell's equations also have something to say about the bending of an electromagnetic wave when it gets to the boundary between media. Okay, and I am hoping that I can kind of get my resources together and make a video about that one sometime a little bit further down the line. Okay, all right. Well, I hope you have enjoyed this video. Thanks for hanging around and to the very end. Again, this is derivability. We do derivations problems from kind of introductory, mid-level undergraduate physics, engineering, and math. Okay, so if you like what you're seeing here, please subscribe to the channel and check out some of my other videos. And as always, in the comments or somewhere, just drop me a suggestion for a future video or other things. I love to hear from you guys. I hope to respond to some of your comments as well. All right, and hang around on YouTube, and maybe I'll see you again here within the next week or so. Have a good one.